Hello, I am Navya Nayyar from Amity University. Today I am presenting our work on causal discovery in education, where we apply deep end to end causal inference to analyze student outcomes using the Open University Learning Analytics dataset. This is a joint work with Dr. Misha Kakkar and Neha Gupta. Educational analytics has a fundamental problem. Current approaches rely on correlation based models that can identify patterns but not establish causation. This severely limits actionable policy insights. Why does this matter? Because effective interventions required understanding true causal mechanisms, not just associations. Correlation does not equal causation, and this leads to policy failures when we misidentify the relationships. So, our research question is: can neural causal discovery reveal actionable educational interventions that go beyond traditional correlation based approaches? We make three contributions. First is this is the first application of DESI model to educational analytics at scale with over 31,000 students. Second, we provide a systematic comparison revealing exactly why correlation based policies fail. And third, we conduct counterfactual analysis to provide evidence based policy recommendations. Our key finding: age shows 10 times more stronger causal effects than correlation suggests, while education's strong correlation actually masks zero direct causal impact. We use Open University Learning Dataset, which contains data from over 32,000 students. After pre-processing for complete records, we analyzed 31,482 students across 11 features. These features include demographics like age, gender, and disability status, social economic variables like IMD band and region, and academic variables include education level, studied credits, course module, and previous attempts. Our outcome variable is the final result. As a baseline, we computed correlations. The heat map shows the relationships among all the features. Education level shows the strongest correlation at 0.157, followed by socioeconomic status at 0.132. Previous attempts negatively correlate at minus 0.118. But here's the problem: the mean correlation is only 0.069, that is very weak. More importantly, correlation cannot determine causality, provides non academic actionable insights, and leads to misleading policy guidance. This motivates our causal discovery approach. We employ DESI, deep end to end causal inference. Why is DESI well suited for educational data? It handles mixed data types, both continuous and categorical. It captures non-linear relationships through the neural network, and it can model unobserved confounders via latent variables. The architecture uses a graphical neural network for structured learning and neural structural equation models for functional estimation, with variational inference for joint optimization. We trained for 30 epochs with a batch size of 256, processing all 11 features simultaneously. The output is a complete causal graph with 53 directed edges and their strengths. To assess policy relevance, we simulated six counterfactual interventions: removing disability barriers, improving education levels, optimizing age effects, reducing previous attempts, increasing credits, and enhancing socioeconomic status. For each intervention, we identify downstream variables, compute effects, apply these interventions to 1,000 students, and aggregate results with bootstrapped confidence intervals. Here's the discovered causal graph with 53 edges. The thickness of the edge indicates the relationship strength. Let me highlight the most important relationships in the next slide. Age to the final result has the strongest causal effect at zero point 0.8. Disability affects multiple pathways: highest education, module selection, and credit enrollment, all with strength zero point 0.7. Socioeconomic status intersects with gender, disability, and credit choices. Notice this important finding: the final result causes future attempts with strength zero point 0.7. The direction is opposite to what correlation suggests. All relationships with strength zero point 0.6 or higher achieve statistical significance with p less than 0.05. Our counterfactual analysis reveals dramatic differences in intervention impacts. Higher credits has an impact score of 52.23, which is massively higher than anything else. That is better than socioeconomic support, which scores 1.06. Education improvement, which scores 0.43, and other interventions are much smaller. The priority ranking is clear. Credit optimization far exceeds socio-economic support, which exceeds education improvement. Now, here's why causal discovery is critical. Look at these dramatic differences between correlation and causation. The H2 result, the correlation is 0.077, but causal effect is 0.80, a 10 times amplification. Education to result, correlation is 0.157, suggesting it's important, but the causal effect is 0, that is a no direct path. Credit to result, correlation is negative, but causation is positive 0.65, completely reversed. Correlation would suggest reducing credits, hurt students, but causally, credits actually help. Disili- Disability to result. Correlation is weak at minus 0.041, but causal effect is strong at 0.60, 15 times stronger. Attempts to result. Correlation suggests attempts predict failure, but causally, results causes attempts. The arrow points the opposite direction. This is the critical insight. Correlation based policies would prioritize education and ignore disability, while causal analysis reveals disability has 15 times stronger effect and education has zero direct impact. Let me summarize the four key paradoxes. The education paradox: strong correlation but no direct causal effect. It works through immediate intermediate variables. The disability underestimation, the weak correlation but strong causal effect. Removing barriers improves outcome significantly. The age amplification, moderate correlation but 10 times stronger causally. And the attempt reversal. Success causes future attempts, not the other way around. Based on our findings, we recommend four priorities. Priority 1, credit system optimization. Priority 2, socio-economic support programs. Priority 3, disability accommodation. And priority 4, the age optimized learning with cohort based programs and flexible scheduling. Implementation feasibility analysis shows the credit optimization has low cost, immediate timeline, and highest ROI. Most institutions can implement credit recommendations immediately using the existing infrastructure with minimal resources but maximum impact. Other interventions require medium to high investment over 1 to 3 years. Our results are robust, statistically validation, 95% confidence intervals from 1,000 bootstrapped samples or relationships zero point 0.6 or higher are significant, consistent across 5 independent runs. The literature validation, 87% of strong edges aligned with educational theories, 78% relative rated possible by 15 domain experts. Robustness analysis, 89% robust to noise and 92% the cross validation consistency. Compared to traditional causal discovery method, DESI offers significant advantages. PC is fast but produces many spurious edges. Lingam and Notios yield very sparse graphs with only 4 to 5 edges. DESI, despite longer runtime, recovers much richer causal structure with 53 edges and supports mixed data types and nonlinearities. Three key takeaways. First is the correlation misleads policy. We showed that age is 10 times stronger causally, education has zero direct effect, and disability is 15 times stronger than correlation suggests. Second, causal discovery enables action. DESI reveals true mechanisms, counterfactual simulations quantify impact, and we get evidence based priority rankings. Third, academic factors matter most. Grade optimization has 50 times higher impact than other interventions, but targeted demographic support remains essential for equity. Now, future work includes multi dataset validation across K 2, 12, community colleges, and MOOCs, longitudinal causal analysis for temporal dynamics, enhanced confounding control through natural experiments, and implementation science with randomized trials and real world deployment studies. In conclusion, this work demonstrates that neural causal discovery can reveal hidden mechanisms, correct misleading policies, provide quantified intervention guidance, and enable evidence based educational policy design. We are moving educational analytics from asking what patterns exist to what actions actually work. Thank you for your attention. For questions or collaboration, please reach out at the email shown. Thank you for your time.